Okay, so good evening, and welcome to the next installment of the SLAC Public Lectures. We're very lucky to have as our speaker today Professor Yi Shui from Stanford University, from the Department of Material Science and Engineering. The topic is batteries. Batteries used to be considered some kind of irrelevant technology, but today we all worry about things like my iPhone is too heavy to stick in my back pocket, my hoverboard is going to blow up, or my Tesla isn't going to make it to LA. And so these issues have become very relevant. And Professor Shui is one of those people who really has just one innovative idea after another for how we're going to make the batteries of the future. He got his undergraduate degree from the University of Science and Technology of China. From there, he went to Harvard, where he got his PhD, and he was a Miller Fellow, one of these prestigious fellowships given by the University of California at Berkeley. Now he's an associate professor here at Stanford, has a big lab with students who keep marching toward the future of batteries. And that's what he'll tell us about today. So please welcome Professor Shui.
Well, it's a great honor to speak in SLAC public lecture. I've been joining Stanford faculty for 11 years. This is perhaps the most prestigious lecture I'm giving. Looking at the audience right here, from just a few high school students I can spot from their age. Quite a number of seniors right here also. So it's really good crowd right here. And I was making joke with Mike. I said, the lecture I'm giving, only 2 words right there, reinventing batteries. From the number of audience divided by the number of words in the title, I probably scored a record, right? So, so it's a great honor, absolutely. From this big crowd of audience, everybody knows how important the batteries is. Might give a few sentences introduction. Let me step all the way back to the time when I was still a kid in elementary school. Right? This is the time you saw this. Oh, this is really big. So I was thinking, as a kid, I say, what's the purpose? First time seeing it, I say, it's for self-defense or something. You carry something like that big. Probably it can serve the function, right? And then it goes smaller and smaller and smaller. So you look at this, you say, well, our semiconductor electronics is getting smaller. We integrate more transistors on there, certainly we can make things smaller. Indeed, the major reason to make it smaller is not our computer chip. It's the size of the batteries right there. Our batteries is getting better and better, right? So, well, you will be wondering whether this trend will go no stopping. No, the history actually reversed, right? So this is what's happening. So from generation 1 of iPhone, right, you feel very comfortable put into your pocket to now iPhone 6s Plus. It's getting bigger and bigger. So what's going on? So you all know the answer. It's the batteries inside. You open the phone, you look at this. This is the batteries. It occupies most of the space. That actually determines how big your phone is. So this is the, from your day-to-day life, you know about this. So many exciting things are happening in the past 10 years or so. This is the DJI drone flying. If you have it, you know it's about 15 minutes, right? So changing battery is a big hassle right there. Tesla. I bet there got to be 10 Tesla from this audience in the parking lot right there. When I come in, I actually saw a number of them. 250 miles range also. That's the problem coming up. Go to LA, not quite enough. Go into the supercharge station, stop for half an hour, then you are ready to go. So how far this can go? And then stationary storage is important. In California, we passed a law. We know we need 50% renewables, right? From solar, from wind, from nuclear. So in order to integrate this into the grid, there are intermittent energy sources. They fluctuate a lot. So grid cannot take 50% without energy storage. So you look at this, you add all these pictures together. This is the picture you are seeing. From the phone, the amount of energy carried in your pocket per phone is 10 watt-hour. Watt is power times hour, well, times time, right? That's energy. That's the unit. Remember, we have 1 billion pieces phones sold every year, roughly. So time together, this is 10 to the 10 watt-hour. It's gigantic. Well, that's roughly 15 to $20 billion industry right now. And the drone is a little bit bigger, 7 times. It's 70 watt-hour. Tesla, 85 kilowatt-hour. So there's a lot more. Assuming we want to have 1 million EV of Tesla right there, this is 10 to the 11 watt-hour, much bigger than the phone can consume, 10 times more. So you need a lot more batteries right there. That's a major motivation when Elon Musk figured this out and say, there's not enough batteries I can buy if the whole world's production is dedicated to me, to the Tesla car. So he's building the Gigafactory, double the world production. And let's look at the grid. So every morning, you woke up, we have about 20 gigawatt of power right there. And then it climbed up very fast to about 30, 35 also. By the time we get to 50% renewable, we need to store this energy. Roughly, you need to build a really big battery right there. That's equivalent to this 1 million EV, 10 to the 11 watt-hour, gigantic. The whole world can go to 100 times bigger than that. So there's a huge demand right there. And then the question you want to ask is, how far the battery technology can go? Can it really satisfy the demands, the application, and all these areas? So you look at the relevant parameters. How much energy you store per unit weight, that's kilogram, and per unit volume, that's liter, right there. For your cell phone, it's probably the liter you care the most. For the car, you care about the kilogram first, and then certainly the liter as well. The cost is the major roadblock right now. So that's why Tesla S model is somewhere around what, $80,000, right? So the Model 3 claimed to be $35,000 and when it comes out. So the cost is a big thing. And the cycle life also, for your car you want 3,000. For your grid storage you want 10,000. Charging rate, everybody wants to do it. Plug it in and take it out. It's all full. Everybody wants that. But it's impossible. So how fast can you charge? So safety is important. You have seen, accidents. So what the battery can be made ultimately safe? Those are the questions we try to answer, and my group, and many research groups around the world try to answer as well. So let's look at where we are right now. What's really needed? Lithium-ion batteries has been the most high-performing batteries in the world, the most well-known chemistry. Let's look at lithium-ion battery cell now and the future goal. This is in the cell level. When I define cell, I mean those cylinder you see, this individual unit of the battery cell you see. This is system level. It's also referred to the whole packaging. If you have a Tesla car, you pack a lot of batteries together. You do grid scale storage. It's the whole system cost. So let's look at energy. Now the cell, roughly somewhere close to 200 watt per kilogram. After 25 years development, we are somewhere around there. We want to get to 600. Why? Because your car will run 750 miles. That would be nice, all the way to San Diego. And you can go to LA and come back, still work, right? No charging. So for the long term, for the short term, I will be very happy we get 500 miles. So double will be good enough. But as a research goal, we might like to target in university, let's do 600. If we fall down, we fall to 500. So fall to a double. That's not too bad, right? So at system level, this roughly cut by half, depending on how good you can do your packaging. The cost, at the cell level, we are roughly $150 per kilowatt hour. System level is 300 to 500. Because you put in all the safety system, temperature control, battery management system, this will add up the cost. We would like to get to eventually system level, 150. That's what Department of Energy calculated. In order to make EV deploy in a big scale, general public can take the cost, and you need $150 per kilowatt hour. For the grid scale storage is the same number as well. And that's cycle life. I mentioned 3,000 and then 10,000 for the grid. So eventually you also want to safety to work out very safe batteries. Looks like you are really working in a domain with multiple parameters you would like to get to. But let's emphasize the most important one first. That's indeed the cost. The cost we still need to cut down quite a bit. We wanted to get to 70, in the cell, 150 system. So you say, how do we do this? We already been doing lithium-ion batteries for the past 25 years. Our learning curve just drive down the cost so much. Can you still squeeze a lot of unnecessary costs to make the price, the cost lower? Maybe getting down to 150 is hard. But if you want to get to that low, looks like the most powerful knob you want to tune is the energy. When to make the energy density higher, for the same weight, same size of the battery, you store more energy, then the cost, dollar per energy per kilowatt hour, will be reduced. So that becomes clear after looking at this and say, well, let's make high energy density batteries with the similar manufacturing cost. Then we can make the cost per energy lower. We can extend the electrical car range. And this revolution, as we are speaking, is really coming. And the transportation in the grid and also getting more renewable into the grid. So that has been really a clear focus for the past 11 years for my group. But let's look at how do we get to high energy. High school physics. I believe everybody understands this equation, right? This is the energy equals to voltage multiplied by the amount of charge. Okay? So I want to get more energy. What do I do? Right? This, and it goes up. High voltage and large amount of charge. And then eventually it's the energy density per weight and volume. I want to pick the lightweight materials. I can store this charge. I want to have small volume. So it's the game to go into periodic table to find what's lightweight. What can you do with that? So now let me come back to really share with you. This is the highest tech and also the easiest way to understand how do you find batteries, right? Materials. Let's look at the cell first, and then we'll come back to look at it. So lithium ion is used, right? This is the cylinder cell. This is what Tesla used. 7,000 of them packed into the S model, right? To produce this amount of energy. You cut it open. This is a jelly roll inside. And then if you look into that a little bit more, and this jelly roll is zooming in one of these, two layers. One is a negative electrode, also called anode. The other is a positive electrode, called cathode. Positive electrode has this aluminum foil. On the surface, you have coating of this particle called lithium cobalt oxide. And the other electrode is a copper foil, about 5 to 10 micron. The aluminum foil similar, about 10 micron also. And having this particle coating. And then you have a separator. It's a polymer. It's a nanoporous, has a lot of pores inside. And you fill in the organic electrolyte. It's a liquid with lithium salt, right? You charge your battery, you're pumping in electrons, it goes to the anode, lithium will come in and store inside the crystal structure. And then when you use electricity, it goes the other way, lithium will come back to lithium cobalt oxide. So this is also called rocking chair of storage. Lithium go in to one side and come out and come back to the other side. So in order to make these batteries to work, just a little bit science on that is a material is so important. This graphite particle right there, labeled as a carbon-6, this lithium cobalt oxide particle materials are important. First of all, they need to move electrons. Electron needs to go from outside and jumping into individual of this particle and meet with lithium ions. The second is lithium ion needs to diffuse back and forth in the liquid and also go into individual particles. You also accompany with this process, there might be some structure change, a little bit of volume expansion and contraction. Because ions, they all have certain diameters. They need to squeeze their way in, right? And the fourth thing you need is, on each of these particle surface, they are soaking into electrolyte, right, for 3 years. Imagine, you sit in water for 3 years, what happened? Well, you get corroded away, right? So the only reason this particle can survive is it has cell passivation layer. It reacts with this organic electrolyte a little bit, forming a very thin layer of coating, let's say 20 nanometer to 100 nanometer also, will protect this particle from further corroded away. So allow you to have this battery running for multiple years. So you need these few things. Now let's come back to look at this basic structure and see how do we get high energy out of it. You increase the voltage. The voltage is defined by these materials. There's actually a limit right there because the higher the voltage, you are going to decompose your electrolyte more and more. We are now already reaching somewhere close to 4.5 watt. The most we probably can do is 5. So we have about 10%. We have about 10% only to go higher. And then you say, I want to increase the energy. What do? I should play with charge. It's the electrons you want to store. And in order to store electron, what do you need to do? Why do you need lithium ion? The reason is electrons all have negative charge. They don't like each other. And then you need to balance the charge with a really heavy positive ions right there. They combine, they become charge neutral, they're happy, you store a lot of them, right? And then, these ions and electrons, when they meet, well, they don't want to meet alone. I often use the idea, I say, boy and girl and dating. You cannot get them to just walk on the road, right? So, and then they need to go to a restaurant. This is the restaurant, so they need to meet. Gigantic, very heavy. So this is your host materials. And they meet right there, okay, charge neutral, fine. So in order to store energy, I want to put in a lot of electrons. That's really the charge carrier doing the work, power your electrical car. Now you want to pick this M, that's the ions. You want the lightweight, the lightest weight, and periodic table is hydrogen, is proton. Atomic weight 1, lithium is 7, sodium 23, magnesium 25. But remember magnesium, aluminum right here. they have 2 plus and 3 plus charge. If you put 1 ions in, they can balance 2 electrons, 3 electrons. So it's good, but there's other consideration. So these are some of the elements you see, a lead acid battery, right? We use lead and also proton to come in to balance the charge. However, the second consideration is the voltage. If you take proton, that's a water, you increase the voltage roughly above 1.5, or you start to split water, generate hydrogen gas. So that's not good. So the voltage of these proton-based batteries is not high enough. But lithium, most electropositive elements allow you to go to high voltage, 4.5. Sodium will be a little bit lower, and then this will be even lower. So you see the reason now, lithium combined with a reasonable lightweight, second to proton, but produce the highest voltage. Why is dominating the battery technology? That's because of its high voltage, plus very lightweight. And now the question is, what about the cost? If I pick lead, so cheap, like $2 per kilogram, I pick hydrogen, nearly free, that's water. So if I put lithium, it gets up to much higher. So when you look at this, you say, my God, this is not sustainable. We'll come back to that topic. But I'll tell you right now, one thing is, lithium cost in the battery is only less than 3%. It doesn't matter yet. It's the cobalt you put in, the graphite you put in, the electrolyte you put in, the separator you put in. That costs more money. Lithium actually doesn't cost that much. So graphite has been used as the negative electrode. It has this joint is this carbon atom linked together to form graphite. It produces this layer by layer structure, right? Between the layer, interaction is weaker. Graphite is known as lubricant. That's because of this layer structure. Lithium can be charged inside. These are your lithium ions, in and out. So you have a negative electrode. And what's the choice beyond graphite? If you look at the new material, silicon. Well, sitting in Silicon Valley right here, every time I see silicon, I get excited. I say, well, that's the whole valley knows so much about, right? So actually, silicon can store a lot more. It's the lithium coming in through different mechanisms from graphite. Lithium coming in, cleave this silicon-silicon bonding and form lithium-silicon bonding. This number, compared to that number, 11 times. And lithium metal itself also store a lot. So we have choices, much, much better choices, 10 times more storage. So why not using this, right? Well, let's look at the cathode, the positive electrode. Lithium cobalt oxide, everybody's cell phone and laptop now use lithium cobalt oxide. And lithium manganese oxide, this is an GM's, the watt, right? It's a lithium manganese oxide for the electric car. And lithium iron phosphate, most of the Chinese electrical car companies use lithium iron phosphate. So they all have this crystal structure, either consists of two-dimensional structure with lithium so-called intercalate in and coming out, or this three-dimensional structure, this yellow ball, or this one-dimensional structure, lithium can go in and out into this host. They're stable. What's the choice for the future? Let's look at this sulfur 8 elemental materials or molecules. A of these sulfur atom forming a beautiful ring. It's like a crown shape, right? And then you react with lithium, produce lithium sulfide, forming a new crystal structure. This is a cubic structure. This is lithium, bonded with sulfur. They're completely different from a ring to a cubic structure. You want to charge up your battery and discharge back and forth. Now you see the problem. They are very different structures. Compared to this, these are two-dimensional structure never change that much. Lithium just come in and out. So that's a lot easier. So, however, if you can make these new materials to work, I told you about silicon, about lithium metal, about sulfur. This is the amount of energy you can store per unit weight. Only consider these active host materials to store lithium. This is current technology using carbon combined with this positive electrode cathode. When you do silicon as the negative, silicon anode, lithium metal anode, you look at the future, you say, I want 3 times more. That's right here. You can find silicon and sulfur combination. You can find lithium metal and sulfur that give you 6 times more energy per unit weight. We do have a battery chemistry that could potentially offer you get to 3x. Sulfur is very low cost. We all know, right? Sulfur is the byproduct of petroleum refining. And there's a lot of that in the mountains of sulfur waiting for you to take away. So why not doing this new chemistry? Now let's look at the learning curve. Past 25 years, we learned from lithium-ion batteries. Those graphite, lithium cobalt oxide, they are considered stable hosts. This is what you learn from past 25 years. Anything that's not stable is considered a failure for the batteries. However, I want to store a lot of charges. I have no choice. It becomes unstable. Unstable from this chemical bond breaking, from the host atoms. All those atoms, sulfur, silicon, are moving to very long distance. You lose control. Big structure change, big volume expansion, 10 times more than the materials you learned from the past. So how do you handle those? Looks like there's no answer for that. 10 years ago. So from all the atomic bonding scale to nanoscale, individual particle, the whole electrode, the whole packaging, just look like a mess. There's no way you can handle those problems. That's why I call reinventing batteries. All the thinking needs to change. The paradigm needs to be shifted. How do you design the materials to solve those problems, to enable new chemistry? For example, today, I'd like to emphasize how important the advanced tools developed, for example, in SLAC, help you to understand the challenge. You can really design the materials. I will use an example of nanotechnology to design materials to enable silicon anode. From 11 years ago when I joined the faculty knowing nothing about batteries until now, we have a commercial product on the market based on silicon, giving the highest energy density. It's also, I believe, from now to future 10 years, silicon anode will be driving the battery revolution. And if you look at Elon Musk's announcement, he also said he's going to put silicon into the gigafactory. So you might see that in the future. For the grid-scale storage, so big, new ideas is needed how to do grid-scale storage. Eventually, battery safety. This is an area, looks like there's not much invention. So we started to look into this area and try to design the battery from the first principle and say, what can we do to make the batteries intrinsically safe? So I'll tell you about 4 small stories. Look at the first one, advanced tools to watch the batteries operation. So if you look at your batteries in your phone, how many times have you thought about, do people understand how batteries work? Right? The first time I worked on batteries, I also asked this question. The answer was no. We don't understand how the batteries work. It's just like a black box. It's amazing. It's working. So X-ray is a very powerful tool. So in about 2 weeks, I need to take my boy to the dentist again. So this is the tiny guy, right, X-ray. So you hit the beeping, and then this is the image coming out. You can tell this person's teeth is not that healthy. There's something going on. So X-ray is powerful for you to see whether there's a cavity, whether there's something bad going on. You see different color right there, right? This tells you what's going on. This is very small, and in a very small room, you can hold this. At SLAC right here, we have a gigantic weapon, right? So that's this. This is gigantic. So this is small. This is about a couple of miles, right? You know, this is like big X-ray machine, right? Shooting. So this is electrons and the high vacuum going in right there traveling, giving you this, eventually the X-ray signal. So this is what extremely bright, has a high intensity, right? Having a high spatial resolution, much more than the dentist X-ray, having a very fast, femtosecond type of resolution for you to study, not just bone now, it's electrons, atoms, molecules, solids, right? Biological cells and so on, and their dynamics. So using this tool, let me highlight one example. You can actually do a microscopy using this X-ray, using actually here and the synchrotron radiation lab, that green pattern you see. This is Mike Tony, this is Johanna, working on this, using the X-ray focus on the sample. You can do the imaging, using this CCD to capture what's happening in the materials. Not only that, you can actually, in the sample you put in, you can put in the real batteries right there. You are doing charging, discharging during this process, watching what's happening. So an example showing you right here, this is so-called tomography, right? Three-dimensional of particles. When you put lithium going in, this is 5-micron scale bar. You see the kind of expand three-dimensionally. You take lithium out, you see this particle now crack. So an example like this can tell us, number one, how do they crack? Where do they crack? And what's the smallest dimension they don't crack anymore? So this teach us a lot. Come back to design the materials. What's the particle size we want? We want them to be small enough, they don't crack anymore. Eventually, this helps you to do battery charging, discharging over many cycles. In combination with a technique like this, let me also highlight another tool. This was available roughly for about 5 years only. At the Stanford SLAC right here, we have one of these techniques. This is a transmission electron microscope. And this is a tiny hole you see right here. This is so-called a sample rod in the holder. You can insert it into this tiny space. This electron beam coming down. This is the important part. You put your sample right there. Then you see it on the electron beam. If we can mount our sample this way, if you zoom in looking at this, we put a metallic probe right there. We can mount our silicon, for stored lithium. We build a single nanostructure battery inside transmission electron microscope, having lithium cobalt oxide, that's your cathode, having a little bit of electrolyte, inserted right here, apply a voltage, now start to charge and discharge your batteries. During this operation, you use electron microscope to watch what's happening to your materials, not only the wires, but also the particle. Now let me show you one of this video. Now notice that this is 200 nanometer scale bar, right? So now I'm going to charge up this silicon nanowires. Lithium coming in, you see it grows bigger and bigger, right? Diameter increase a lot. And the surface coating of copper is broken. So we learn a lot. We now know why silicon for so many years couldn't work as a battery electrode, because it just breaks everything surrounding it. So how can you make it to work? Not possible. And not only that, the silicon, this silicon structure, when they store lithium coming in, they commit suicide. Let's look at it. This is a particle, 800 nanometer to start with. You put lithium in, you see this crystalline silicon core string. This is a lithium silicon alloy start forming. At the beginning, all very happy, growing bigger and bigger. As soon as it gets to a certain size, it finds out itself, the stress, the strain is too big, so it has to commit suicide in order to relax the strain. So this is broken. So after that, what happened? The batteries die, your cell phone, no signal, no power anymore, right? So that's the consequence. Because this particle broken apart, they are not connected electrically anymore. So we learn a lot using these two techniques, help us to guide the material design, what's the critical breaking size, 150 nanometer for the particles. This guy is too big, 800 nanometers cannot survive. Nanowire about 300. Now knowing this, we know small things are great. They need to be small enough. Now let's design the materials to make it to work. So this is the phenomenon I was describing. Silicon take a lot of lithium, 11 times of graphite capacity. Volume expansion to 4 times. Imagine that, that's a lot, right? If you look at the furniture, I remember when I was a little kid, summertime come, my hometown was very hot during summer, and then winter time it gets cold. It goes through this cycle, hot and cold, and the furniture actually cracked. That's only probably 10%. You're talking about 400% right here. How do you avoid breaking? How do you build stable so-called solid electrolyte interface? Remember, individual particle surface soaking into electrolyte for 3 years. For electrical car, you want 10 years. For grid, you want 20 years. How do you make it stable if there's a volume expansion during charging? And during discharging, volume shrink. So no stable interface, surface right there. How do you do that? So we learn a lot. So let me give you a quick 10 years of research, right? Into 2 slides. Well, we use nanowire. They're small enough, they don't break. And then we do coarser, it's more stable. And then we do hollow, even more stable, but no stable interface. And then we design double wall hollow structure. It just keeps coming. Now we are 11 generations. So that's my 10, 11 years at Stanford. So that's what I did. So 2 slides. But let me highlight a few to share with you the thinking. What's the design principle right there? We know the volume expansion happening, it breaks. So small things don't break. Number 1, you need small guys. And then there's, because of volume expansion, it's going to squeeze the surrounding environment. In order not to break the surrounding environment, what do? Leave some empty space right there. How do we do that? We take a silicon nanoparticles, 80 nanometer in diameter, small enough they don't break anymore. And doing a very advanced nanomaterial synthesis, we can design empty space right there. Just fits exactly to accommodate this volume expansion with a conducting carbon coating right there. So make sure this expansion don't crack your coating. We pack all these particles together, hundreds of thousands of these particles, forming secondary particle like this. Why do we want to do that? That's because individual nanoparticle, the surface area to volume ratio is too big. They're going to react with electrolyte, consume too much electrolyte. Pack into secondary particle, electrolyte only wets outside. We reduce the surface areas. We are also having something called increased mass loading because we pack so many materials together efficiently onto one electrode. So we can have more capacities to store lithium. And this help dense packing, so-called the charge storage capacity per unit volume can go up. If they don't pack very well, occupy too much volume, even the individual particle can store a lot of lithium, but you waste a lot of space, so that's not good. So we designed this. It's called permanganate-like structure. So we made this, right? So this is a nanoparticle packed into about 1 micron in diameter. This probably have 50,000 of nanoparticles in there. Once you get to here, there's a few hundreds of thousands of particles all packing together. Under electron microscope, let's look at it a little bit more carefully. You see the empty space. This dark space is empty, is air inside. This bright is the silicon nanoparticle. You see each one of them having some empty space. Isn't that amazing? Now nanotechnology can do this. I have 100,000 of these particles right there. Each one of them will have their own space. When they volume expand, they expand. They don't crack the environment. So, and now you use this to build a battery electrode. You do the coating. You put a lot of material onto metallic foil, right? You start to measure its capacity per unit gram of silicon. You see this is the capacity of silicon and CO2 is 2-hour charging, discharging speed. It's stable. If you don't have this packing without empty space, this capacity will decay fast. And also using this structure, these parameters called Coulombic efficiency, that's this plot right here. What does it mean? Let me explain a little bit. You know, when you store electrons into batteries, you put 1,000 electrons in, you need at least 999 electrons coming out. You're allowed to lose only 1 out of 1,000. This is the one we are getting close. 99.87, you want 99.9. What does this mean? This tells you if you lose 2 electrons every time, there got to be side chemical reaction happening right there. If it's a 98%, you will calculate right away. Capacity is 1. Next cycle is 98. Next cycle is 98 times 98. Next cycle is 98 times 98, 98%. And after 100 cycles, you don't have capacity anymore, right? So you need this high Coulombic efficiency. This is an indication we can reduce side chemical reaction by packing this particle into the secondary particle, reduce the surface area effectively. So we have also high capacity loading. Well, after this was 2014. Well, I've been in faculty for 9 years now. Our generation 8, after that, looks like it's done. So we solve all the problems. No, not yet, not yet. So it all the way come back to as a cost. Nanoparticle, we still need to learn how to make it cheap enough. It's still high cost. Bigger things are cheaper. If you take silicon, right? Anybody know solar industry? You know silicon. What's the silicon cost right now per kilogram?
Oh, per kilogram? You tell me.
Well, you're talking about probably in the order of $10 or less right now, polysilicon, right? But if you have nanoparticle, how much does it cost? A few years ago, as the cost is as high as gold, right? So that doesn't work. So it's now cheaper. In the future, it probably can get cheaper for the nanoparticle. But let's see, if you can do 1 to 3 micron, it's as cheap as graphite or cheaper. It stores more charges, store more energy. So if you can get micron particle to work, that's a big win. But for 10 years, I don't believe, I have never believed micron particle to work. But in the back of my mind, I always ask myself, if I can make it to work, it got to worth it. How do we do it? I was telling you, big guys will break, right? They break into pieces. The batteries die. They also, in contact with electrolyte, build this so-called solid electrolyte interface, side chemical reaction compound. Battery die very fast. However, imagine if you can come up with one idea to make it to work. With all these 10 years learning, it's worth it. So the idea comes. So that's this. So you have micron particle. For about 10 years, my group learned a lot. How do I build a cage, build a loom for individual particle? What if I can build a cage right here? This black color one is robust enough. If this micron particle break, they break inside, they cannot fly away, right? This cage is electronically conducting. Then I might have a chance to get it to work. Even they break inside. They don't go outside, so it's still my stuff, so might work. Let's find the strongest cage right there. So it turned out to be in the past 15 years, right, you heard about Nobel Prize of graphene. Graphene is very strong mechanically. It's conducting electricity. So if you can build graphene, multi-layer graphene, that's basically graphite, right? And when volume expansion happens, you leave some empty space right there. And if you don't leave that, you know, even graphene cannot hold it because volume expansion is 4 times. It will break your chemical bonding of carbon-carbon. Leave some space. And this graphene, we expect they're strong enough, they kind of hold their shape, you know, try to keep all the silicon inside. So we made this. Silicon micron particle, we developed synthesis. Doing a nickel coating, get a little bit of carbon coating right there. 450 degrees C, not too high temperature, turned out to be this nickel is a catalyst to grow carbon into a graphitic carbon. Actually, nickel leave the empty space. You see now there's a cage right there surrounding this black dark color of silicon. And if you go to high resolution of transmission electron microscopy, you can tell it's a graphene packing right there. So let me show you a couple of video to tell you how amazing this graphene cage can be. It is all type of carbon. If you know a little bit about materials, well, carbon can be very expensive one. What diamond, right? Can be very, very, cheap one. It's coal. Somewhere in the middle is graphite, and then there's amorphous carbon. It's all kind of carbon right there. So easily, when you make carbon, it become amorphous. You can build this amorphous carbon, a shell. It's a cage. You can also have this graphene cage. Let me show you the difference is dramatic. Somehow this video format is, okay, show up, that's good. So this is the one, that's graphene. Inside electron microscope, we use this tip to push on this graphene. Now you see this hollow shell, right? This is really thin, now bounce back. It's actually very resilient, very flexible. You push on it, it comes back. You retract the tip, it comes back. You can do this multiple times. This made us think this is a great material, function as cage. If silicon break inside, it's kind of like silicon bounce onto the graphene, and push the graphene, graphene doesn't break, and then get contained inside. But if you look at amorphous amorphous carbon, that's right here. A push on this amorphous carbon, now you take it back. You see, it doesn't bounce back anymore, it's broken. So using graphitic carbon become important, it's conducting. So we actually use this. We build batteries, right? So now capacity is stable with this micron particle. Without this cage, you see control sample will just capacity decay very fast. And not only you have a stable capacity, if you look at the electrode on metallic foil, this is a cross section. And in the beginning, 15.5 micron becomes 17.2, only expand a little bit in the electrode level. But the bare silicon particle without this graphene cage will be broken, expand a lot to 30 micron, 3 times. This is the killer to your battery. You don't want your electrode to expand. If electrode expand, it's going to squeeze your packaging and leak out, and your packaging will be broken. You leak out the electrolyte. That's dangerous. So this is now also solve the electrode level expansion. So before my lecture, there's somebody asking me, are you going to talk about commercialization? I will just show one slide. So this is not for advertisement, just for showing you. So 2009, I found this company called Amprius. Indeed, we just have board meeting this afternoon. It's looking quite exciting, the company's progress. 2013, we start to have batteries sold on the market, continue until now. So we are generating some of the highest energy density batteries in the world. So this is start to use silicon. Now it start to get into the world, become real. That's why I have the confidence from now to next 10 years, silicon is the driving force. Replace carbon, blame is carbon, replace carbon. Eventually, get your Tesla car to run not quite 500 miles, probably get you somewhere around 450 miles. Possible. So this is the materials now becoming possible. So with this, indeed, these other chemistries, I won't have time to talk about. I mentioned lithium metal coming in will make it even bigger. There's a sulfur coming in can make it bigger. And this material is also full of challenges. Learning from silicon, I think this possibility we can make those materials to work as well. Beyond 10 years, lithium metal might come in, sulfur might come in. So we have a great path to realize the high energy, for the transportation. This is highly, highly promising. Let me switch gear, talk about grid scale storage. Grid is big. So I mentioned solar, wind, integration into grid because of intermittence in nature. You need to smooth out the fluctuation from second to minutes. You need to be to the load shifting in hours to days. You need batteries or maybe some other technology. Let's look at the current technology, right? The most well-known one, the whole world actually is the so-called pump hydro. You pump from water right here, pump to a lake, right? It's a dam right there, and then during this for storage. When you use electricity, you let the water flow down and regenerate the electricity. Energy efficiency is not that high though. We cannot do this in California. We don't have enough water to even do it, right? So this is a very geographic, location dependent. But indeed, this is the the most popular technology. Other technology only have this amount, right? This from 2010. Certainly, this number now changed. But the scale, relative scale, doesn't change that much. Now let's look at batteries. Will battery make it? So you wouldn't like to connect this. Let's say 10 years ago, battery is so small, everybody used. With this big problem, how big that is? I use a gigantic right here. Let's look at California. I mentioned roughly 10 to the power 11. That's roughly about 50 gigawatt hour also. I want to use this number to compare the annual world production of lithium-ion battery as we are speaking in 2015. It's only this number. If the whole world shipped this battery to California, still not enough yet for us to power the grid, right? The Tesla's Gigafactory will double this capacity, another 35 gigawatt hour in Nevada. So what's the scale? Somebody mentioned a football stadium. So this is a Stanford football stadium, right? So very big. In order to power California, imagine Stanford president is willing to donate this football stadium to hold the batteries. We will need to build a battery roughly filling from here, the whole thing, up to about half. Gigantic battery we needed. So should we think about other ideas for doing batteries? So here's one. In order to fill a football stadium, the easiest way is actually liquid, right? We know. So this is a flow battery called redox flow. What's the idea? You have this tank right here to store a liquid. It's an electrolyte. Inside, this redox molecule can do oxidation and reduction reaction. Once you have this electrochemical reaction possibility, then you can store energy. This is a famous redox couple called vanadium. Vanadium from oxidation state of 5 plus to 4 plus, 3 plus to 2 plus. One liquid is going from, for example, this is 3 plus to 2 plus. That's right here. That's analyte. This will be here. So you flow the liquid in. This is your batteries, and you store energy. You store this liquid. In order to use the energy, you flow it back, and that's a highly scalable method. However, it's the cost. Vanadium's cost. You need this membrane, ion conducting membrane to be low cost. Naphthalene is the one used right now, produced by DuPont. High cost. And you have two liquid flowing with a very thin membrane. If your pressure is not balanced, your membrane is broken, and then you need to go in to fix it. High maintenance. And also, the solubility of this molecule is not that high. It's about 1.5 molar only. So if you invest a lot of money to build this battery, building the pumping system, putting the big tank, that's your capital investment. You want as much energy out as possible. This is only 30 watt-hour per kilo. Similar as your lead acid battery is too low. Cost per energy is still very, very high. So we look at this, we say, can we find a new redox chemistry that has very high solubility. So that's this guy called polysulfide. This really interesting story in my group work called sulfur. I told you sulfur cathode. The most painful problem we are dealing with sulfur cathode is lithium and sulfur react forming so-called polysulfide compound. It's so much soluble into the electrolyte, and then we lose materials into liquid. They cause capacity decay. Then one day one of my students come talk to me, and then we recognize, well, if the solubility is so high in that liquid, why don't we use that liquid for the flow battery? It's the best. So that's right here. You can get to 10 molar solubility for the polysulfide. Well, this is vanadium redox flow, 1.7 molar. Now you see right away, if you have 1.7, I can get to 10. I have 5 times, 6 times more solubility. My energy density will increase 5 to 6 times more. If I do the same amount of investment on the pumping and piping and big tank, my cost per energy is reduced by, by 6 times, right? So you take lithium metal, you throw this liquid in and out into this battery. This is big tank you store. This is a beautiful thing using lithium metal. You don't use 2 liquid, you use 1 solid, 1 liquid. You don't have the mixing problem anymore. You don't want 2 liquid to mix, right? Now solid, then react with liquid, produce this yellow color. It's a cell passivation layer. It stops after a while to make this interface stable. It's conducting lithium back and forth. It's your ionic conducting membrane. You get it for free, so you can go to low cost. So we build these batteries. This is those dark liquid. As soon as you pour into this flask, these 2 electrodes right there, it start to work for a long time, run for a few thousand cycles. There's still some challenges we need to solve, particularly on the lithium metal surface. But other than that, I think this has a great hope to impact the grid scale storage, reduce the cost low enough. Sulfur is low cost. And then I know some of you is going to ask me, what about lithium? Do we have enough lithium right there? It's worthwhile to do all this research. This is our global reserve, 40 million tons of lithium. How much is the 40 million tons? It's very, very heavy. So let's calibrate ourselves, right? It produced 10 billion Nissan Leaf. Nissan Leaf is 24 kilowatt hour of batteries. 84 miles range, contain 4 kilograms of lithium in the batteries. So we got 10 billion. Is 10 billion enough? We got 7 billion people in the world, right? How many cars do we get running after 100 years?
3.
Yeah, we have a billion car running right there roughly, right? So this is a good number. So we have a long way to go. 2009, lithium production, 22,000 tons. Can produce 23 million Nissan Leaf. So that's great. So I'm not worried about lithium yet, right? So what about Tesla? If everybody want S model, 85 kilowatt hour. There are 2 red color Tesla parking outside. One belongs to me. So 3 billion of them. So big number. What if we consume all this lithium? What do? We go to ocean. So ocean concentration is low, 170 ppb. But total number is gigantic. We need to learn how to mine lithium from ocean. I just started a project on that 2 weeks ago. Looks like we are getting great data. We can get lithium out of ocean. So if there's a chance for the future public lecture, I will show you how we get lithium out of ocean. That's a standing invitation, probably. So for the grid scale, lithium is, well, we consume electricity somewhere around 4 terawatt. I assume I store the whole world's electricity for 6 hours, so that's 24 terawatt hour. Our lithium reserve, good for 240 terawatt hour, 10 times of that. So it will take multiple years, I think, probably not even within my lifetime, to worry about we don't have enough lithium. However, we do need to be sensitive where lithium is. there's a geopolitical consideration as well. That's about my pay grade to address this problem. So at last, let me show you one more thing, safety. Safety eventually is very, very important. So let's look at some of the safety instances. You know about the Boeing 787, right? You know about electric cars. You know about laptop. This is the hoverboard, right there, just mentioned, recently. So these all show, safety accidents. So let's come back to look at the lithium-ion battery. This is the basic structure I show you. It got a metallic foil, this side, another one this side, have this particle coating with the polymer separator right there, with organic electrolyte. That can catch fire, they can burn. So what happened? What's going on with those batteries right there? Something is happening called shorting. It can be external short, right? When you have accident, something bump onto the battery causes external shorting. You can also have the internal short that's due to you don't control your charging right. You overcharge, you build lithium dendrite, shoots out from anode to cathode. Or there's a defect right there, this metallic particle during manufacturing embedded inside. That can easily cause shorting, induce the dendrite growth. And also charging in cold weather. So when you go for skiing, don't charge your battery while you are skiing using, you all have the experience if it's too cold, actually your cell phone turns off automatically because it's too cold. And then the impedance is too high, so your battery doesn't work. So don't force your battery working in the cold temperature. So no matter what's the reason, somehow this is something happening. If you cause shorting happening, you store a lot of electricity. And then the current will passing through this metallic foil, through this shorting. You have fast release of battery electricity. What happened afterwards? It heats up your batteries. And then there is a few things happening. When you heat up to roughly about 90 to 120 degrees C, each of these particle surface, this solid electrolyte interface will cell decompose. It's not stable at that temperature. It's exothermic reaction, release more heat, right? So in this moment, still not catching fire yet. But once it go up to about roughly 180 degrees C, now this is something you don't want your battery to go to. This is the oxide. This lithium cobalt oxide carry a lot of oxygen, will react with the organic electrolyte like crazy. And then this goes through the thermal runaway. You don't have control anymore. It got to catch fire and then bad things happen. So now looks like the key thing is, well, let's protect our battery. Let's look at in the past how people do it. Well, let me build a strong case, right? Tesla needs to do that. Once something bump onto my car, make sure it doesn't cause, the battery deformation, cause shorting. Or internally, let me do something. Make sure my manufacturing is high precision. Make sure my balance my negative and positive electrical relative capacity right. They don't grow dendrite. Make sure I have a good BMS, battery management system. Don't overcharge my batteries. Make sure I put in a fire retardant. If something bad happens, they don't catch fire. I put a lot of fire retardant in there. But these only solve the problem only to this level, not that level yet. So you still see batteries catching fire. So we have been thinking, is there another way? Looks like if bad things happen, shorting is going on, the batteries heat up. What if you prevent the batteries heat up to the dangerous temperature? Then you're fine. Right? Can we keep the temperature below this? The reason this go up to this high temperature is because that shorting causes electricity release. So let's don't release the electricity. How do we do it? So we invest something we call a reversible thermal fuse. It's actually a polymer layer coating. Let's highlight here. On this metallic foil, we put in a thin layer coating with polymer with these conducting particle. We call it nickel nanospikes. They are connected together forming a pathway, conduct electricity. This polymer, the blue color, is insulating. Once you have expansion happening due to thermal heating, and it will pull this particle open, right? It becomes an insulator. If it becomes insulated, you have shorting right there. This metallic foil is not connected with this particle or battery material. This electron very hard to leak into metallic foil and pass through the short. So you don't have big current passing through your battery, so you don't heat it up that much. So we'll build this nickel nanospide and make it stable with a layer of graphene, forming this flexible layer. Now this is key data. This is polypropylene polymer, well known, embedded with 30% by way of nickel nanospide. You heat it up 95 degrees C. You see the resistivity suddenly increase by 8 orders of magnitude. It becomes an insulator. From a conductor, become an insulator. So we test this out. If you blow the heat gun right here, this becomes not conducting anymore. This LED goes off. So we build our batteries, in the regular temperature, you can get capacity out. Once you heat it up, there's no capacity coming out. So you have a thermal fuse right there. It's reversible. If the temperature comes back to room temperature, it works again. So an idea like this might help us solve the battery problem in a very different way, the safety problem. Let me summarize. I was showing you 4 examples. There's a lot of opportunity to reinvent our batteries, eventually reaching this goal of energy, density per unit weight, and the cost as well, because energy is higher. And we improve our material to have long cycle life. We can impact the safety. Let me end my talk by thanking all the heroes in my group. PhD students and postdocs, they are very, very talented. Some of them are sitting in the audience right here. All this funding support collaborators from multiple years. And I would like to thank you for your attention, and we'll be happy to take any questions you have.
So this has run a little longer than our usual public lecture. Probably some of you have to leave. So let me just give a few moments, people who have to leave, to go out, and then we'll take some questions. Now, for the questions, there are some of Professor Shui's students have microphones. Please wait until you have the microphone before you ask your question so that the question can be on the videotape. And we'll just take a few, but I'm sure many of you have questions. So please, who has a question? Here?
Thank you for the presentation. So I work in the solar power industry, and everything's about commercialization and cost. The safety as well, but specifically with some of the inventions that you discussed, whether it was innovations in materials, you mentioned briefly in your presentation that the manufacturing, for instance, the graphene container and leaving the gaps. Are you seeing progress in the lowering of the cost of manufacturing of those more complex materials?
Yeah, good question. We produce those very fancy structures through a multiple step of processing. Indeed, that's something we need to work on in the industry scale. The materials coming in, silicon, micron silicon is low cost, carbon cost is low, but we want to make sure processing cost later is low as well. This is something my startup company, Amprius, is working on, try to get things under control. Yeah, you're absolutely right. From the lab into the commercialization, there's still multiple steps to go.
Yes, sir. Thank you very much for the presentation. It was very, very excellent. I did have a question. You have like maybe a laptop battery, for example, when these things are brand new, they're good to recharge for so many times and you have to get a new battery. My question essentially is this. As battery technology evolves, I get to a point where you have a longer charge at the beginning of the life of the battery. It can only be recharged so many times. I'm wondering if maybe with this new graphene material, enhance that pattern so you have a battery that can be charged, if it can hold the charge for usage longer, you don't have to charge as many times and the battery lasts longer. Is that correct?
That's absolutely correct. If you can store more energy for a given size of the batteries, indeed you don't need so many cycles.
Yeah.
Because every time you use it, it's going to be longer. That's absolutely true. Yes.
Thank you.
Thank you. Hi, fantastic lecture. I really appreciated you taking your time to present your ideas with us today. I'm very interested in flexible batteries, and I'm also very concerned with the safety of batteries over time. Do you think that the way that flexible batteries absorb impact will contribute positively or negatively to their safety as they permeate the market?
The flexible batteries?
Yes.
So flexible battery referred to for some of the audience is you can bend, you know, to the degree, even a crazy thing like you can stretch. That do create concern because of the bending motion and the material, relative material moving, whether there's possibility that can cause shorting or not. That's indeed one major thing people need to take care of, is to have the flexible battery not too short. That's why you look at flexible battery, the energy density per unit weight or per unit volume is lower, because you need to build in the assets of protection. Maybe your separator needs to get thicker, and there's many considerations to make things, make battery flexible. So for many applications, for transportation, I don't think you need flexible batteries. You know, for your cell phone, you don't need it yet. Flexible battery might be needed is when you have some of the valuable device application, that's the time you might need it. It's not clear at this moment the future of flexible batteries. I don't think people figured that out yet. So I cannot make more comment beyond that.
Thank you.
Anyone over here?
Can you sort of calibrate the difference between sort of having a really good handle on the materials you'd like to have and use versus the, you know, yeah, we can make this in the lab, but gee, we don't really know how to make this in any quantity, right? I mean, I want to distinguish between we really, really know the right thing, and if we could only make it, we'd be good, versus we still don't know exactly what the right materials are.
Well, this is an outstanding question. So I wish I know. You know, you're asking if I know this material, this design work, not only work, but also can be made in a large quantity, then you are a big winner, right? So this is a learning curve. I spent 10 years trying to learn about this for a problem like silicon anode. It spent so much. At the beginning, I never consider whether it's scalable or not. I want to find I can make it to work first because it's too hard. So I don't want to work under the constraint of scalability yet. But after 6, 7 years, I slowly put into the constraint. I want something to be scalable. So that's the sequence I learned. I don't think anybody can see that so clearly in day one. I wish I could, but I just can't. So, but it's absolutely a good question. But how do you shorten this, the time of going from make it to work and make it scalable? I think the industry and university and national lab need to talk very often. they need to beat on each other quite a bit. So oftentimes I'm excited. I say, this is working, but I go out to talk to industry folks, they beam it, and then I come back, I think. I'll go out again, they beam it again. So every time I grow. So this process needs to happen fast in order to get the answers you mentioned.
Okay. So let's take just 3 more questions. There are 2 here. Sir, go first.
Thank you. There's probably a lot of electric car owners here. I'm one of them with a Leaf. When you speak of charge cycles, you do complete charge-discharge. What would it be if you only went halfway and recharged, or partial recharge?
Your cycle life goes up a lot. So when we do the lab testing, we are pushing our materials to the extreme, the hardest. But when you really use an electric car, you are not going to do it, right? So when you charge your car, indeed, when I charge my car, I don't charge it to full. Actually, Tesla will tell you it's better to do 90% full and don't go to 100%. But don't empty it either, because when you go to the 2N, that's oftentimes it's a lithium dendrite plating coming out, charge it to the full. If you go to the completely empty, structure change is too big and the materials level, so that reduces your cycle life. So if you do 50%, you go from let's say 30 to 80%, your battery cycle life will be amazing.
Once again, I'd like to thank you so much for the talk. With regards to grid storage, do you see more of a larger number of smaller batteries being held by homeowners with their own personal solar networks, or larger batteries and smaller numbers of them being held by companies such as PG&E with huge solar farms?
So, well, that's an interesting question. So, I think for us here in United States, we can have both. The reason is we have individual house owners, so many family, but this doesn't work in China, so there's no very few individual house owner. So I would say distributed. I have a discussion with probably one person in the audience sitting somewhere from the state grid from China, and comparing a US and China model. So in the US right here, I will be willing to install a Tesla's Powerwall in my house. I think this individual small size battery as a distributed sources model will work here combined with solar. And then the bigger scale, right, and here will also work, much bigger, the battery farm. You can have a battery farm as well. But for countries, for many European countries, if they live in a city, those places, doing a home, individually owned battery will be hard. You need enough space. So that's probably it. I think both can exist depending on the country. Yeah.
So last question, this fellow down here.
Hi, very interesting talk. Appreciate it very much.
Hold the microphone, please.
Oh, okay. Can you hear? Thank you very much for the talk. My question is, I was wondering if maybe you could just say a few words about what the competition's doing. Are there other areas where a lot of progress is being made that, let me say, is different from what you're doing?
So I just talk within the battery space. So I only give you several examples. Of course, there are a lot going on in the world. So there's, for example, grid scale storage. I only show you one example of a chemistry. I have 2 other very promising battery chemistry as well, working in my lab using aqueous solution for the large scale energy storage. And then you look at other places, there's other chemistry as well, also pushing very hard. The answer is yes, there are a lot of I think, friendly competition, try to make different materials and chemistry to work. They all have quite a bit of promise right there as well. But for the transportation side, I think I still strong believer is the silicon for the coming 10 years. And going to so many battery conferences right now, partially because of what we did at Stanford SLAC right here to show silicon is so promising, and also Amprius demonstrate highest energy density batteries in the world. So now you look at the major battery player, they all start to believe in silicon should work. So they all have a huge effort to push silicon into their batteries. Yep.
Okay, let's thank Professor Schrader.
Thank you.